Hi everyone, myself Krishnudu, Assistant Professor of Physics, Department of Science and Humanities, MLR Institute of Technology. In continuation with previous topic, today we are going to discuss about one of the most important topic, that is Fermi-Dirac distribution function. In this particular session, we are going to cover introduction to that Fermi function. After that, we are going to discuss Fermi-Dirac distribution function. After that, analysis of Fermi function, and finally its applications. So now coming to the introduction. So before going to discuss about Fermi-Dirac statistics or Fermi-Dirac distribution function, we need to know about different types of statistical distribution functions that exist to explain the behavior of particles. There are different types of particles based on their spins. So to explain about their motion and their properties, different statistical distribution functions are there given by different scientists. One of them is Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics is applicable to all types of particles having integral spins, half integral spins as well as zero spins. The second statistical distribution function is Bose-Einstein distribution, Bose-Einstein statistics. Bose-Einstein statistics deals with elementary particles having only integral spins. And now the third one is Fermi-Dirac distribution function or Fermi-Dirac statistics. So Fermi-Dirac statistics deals with elementary particles having half integral spins. Fermi-Dirac statistics deals with the particles which are having half integral spins, and generally the particles which are having half integral spin are called fermions after the scientist name Fermi. Fermions are identical and indistinguishable. Fermions are identical and indistinguishable. Indistinguishable means even though the position of particles is interchanged, the properties of the system does not changes. That is why fermions are said to be identical and indistinguishable, and these fermions obeys Pauli's exclusion principle. So according to Pauli's exclusion principle, no two electrons having same set of quantum numbers cannot occupy the same energy state. To occupy the same energy state, the two electrons at least they should have different spin number. So that is the statement of Pauli's exclusion principle. That statement will be obeyed by these particles called fermions. Next, already we know fermions are having half integral spin, and wave function representing fermions are antisymmetric, and then there exists weak interaction between fermions. So generally there exists interactions between elementary particles. Between some elementary particles some interactions will be there, but whereas in this case between fermions there exists weak interactions, and the uncertainty principle is applicable to fermions. So we know uncertainty principle. It is not possible to measure precisely and simultaneously both position and moment of the particle. So that is uncertainty principle. So that uncertainty principle is applicable to fermions. And finally, energy states of fermions are discrete. Discrete means quantized or not continuous. And finally, coming to the examples. So the particles having half integral spins comes under fermions. So electrons comes under this category, which are having a spin of either plus half or minus half. So that is about the basic properties or characteristics of fermions and the basic introduction about Fermi-Dirac statistics. Now we are going to discuss about Fermi-Dirac distribution function, and hence later we are going to know the basic meaning of Fermi level and the importance of Fermi level. Now Fermi-Dirac distribution function. So Fermi and Dirac, these are the two scientists, they have derived one expression in order to study the behavior of elementary particles having half integral spins. That expression is given by this equation. F of E equal to 1 by 1 plus exponential of E minus EF by KT. Here f of E is nothing but probability of occupation of electrons in an energy level having energy E. F of E is nothing but probability distribution function. Probability distribution function. It gives information about the probability of occupation of electrons in an energy level having energy E. That's why it is written as F of E, or occupation probability of electron in an energy level E. It is given by this expression 1 by 1 plus exponential of E minus EF by kT, where EF is Fermi energy or Fermi level. EF is Fermi energy or Fermi level, which we are going to discuss elaborately in the coming slides. And in this expression, small k is Boltzmann constant, which is given by this value 1.38 into 10 power minus 23 joule per Kelvin, and whereas capital T is absolute temperature in Kelvin. So that is about Fermi-Dirac distribution function, which is derived by the two scientists Fermi and Dirac in order to study about the behavior of fermions, or the elementary particles having half integral spins. Now we are going to analyze Fermi function. So how to analyze Fermi function? So particularly we are going to analyze the Fermi function at two temperature. First we are going to analyze Fermi function at T equal to 0 Kelvin. So at T equal to 0 Kelvin, the first condition is if E less than EF. If E less than EF. So capital E is nothing but energy in which the particles are occupied. Energy of the energy level. What is EF? EF is called Fermi energy. EF is called Fermi energy. So now if the energy of the energy level is less than Fermi energy, in that case what happens to the Fermi function? That we are going to study. So basically if E less than EF, in that case E minus EF becomes negative value. Using that in the Fermi function, F of E equal to 1 by 1 plus exponential of E minus EF by kT, where if we use E minus EF as a negative number here, the expression will become 1 by 1 plus exponential of minus infinity. So we know the value of that is 0, e power minus infinity is 0. So now this expression will become finally F of E equal to 1. What does the meaning of F of E equal to 1? So occupation probability of energy level is equal to 1. Means all energies having energy less than Fermi level are occupied. All energy levels having energy less than Fermi energy are occupied. So that we are going to see in the next slide. We are going to see it pictorially in the next slide. Now case 2. At T equal to 0. At T equal to 0, another condition we are taking. If E greater than EF. If energy of the energy level is greater than Fermi energy, in that case what happens to Fermi function? So in this case basically if E is greater than EF, E minus EF becomes a positive number. Using this in this expression for Fermi function, F of E equal to 1 by 1 plus exponential of E minus EF by kT, we know 1 by 1 plus exponential of plus infinity, it will become plus infinity. E power infinity is infinity again. So finally this expression will become F of E equal to 0. So what is the meaning of F of E equal to 0? Occupation probability of energy levels is 0. Means all energy levels are empty. F of E equal to 0 means all energy levels are unoccupied or they are empty. That is the meaning of F of E equal to 0. So how to conclude this condition? At T equal to 0, when E greater than EF, all energy levels above Fermi energy are empty. All energy levels above Fermi level are empty. That is the conclusion from this second case. So first second cases are considered at T equal to 0 Kelvin. Now the third case, what happens when we increase temperature of a substance? So when we increase temperature of a substance, what happens? That is what we are taking this condition. At T not equal to 0, if E is equal to EF. At T not equal to 0, if T equal to EF, in that case what happens to Fermi function? So using this condition in this standard expression for Fermi function, so we will get this expression 1 by 1 plus e power 0. So e power 0 is 1, and finally occupation probability will become 1 by 2. So how to understood this value? At any temperature other than 0 Kelvin, the probability of occupation of electron in an energy level is equal to half or 0.5. So that is about the third case. These three cases we are going to see pictorially in this slide. So particularly we are talking about the behavior of free electrons in metals, because metals are having plenty of free electrons. Electrons are nothing but fermions. So now we are studying about fermions inside metals. So one metal we have taken, and this is the area where there exist so many energy levels. Among all these levels, one energy level we named as E suffix F, that is Fermi level. So using the previous three cases, or by considering the three previous cases, we can say that at t equal to 0, all energy levels below Fermi level are occupied, that is f of E equal to 0. At the same condition, if E less than EF, at the same temperature, if E is greater than EF, in this case f of E equal to 0, all energy levels above Fermi level are unoccupied. So the third case we have seen already, at T not equal to 0 Kelvin, at any other temperature, at temperature T greater than 0 Kelvin, what happens? So when we increase temperature, so generally thermal energy will be supplied to particles which are occupied below Fermi level. So as a result of that, what happens? Transition of electrons takes place from lower levels to higher level. So first, which electrons will move? First, electrons which are in the energy level nearer to Fermi level will move. So like this. So this is how the transition of electrons takes place from lower level to higher level, or filled states to unfilled states. So from this discussion also, we can give one more definition for Fermi level. The energy level which separates filled and unfilled states is called Fermi level. So this is the level which is separating filled and unfilled states. All these are filled states, all these are unfilled states. That is one more definition for Fermi level at T equal to 0 Kelvin. So this is the plot which we have drawn at T equal to 0 Kelvin. So actually graph is drawn by taking f of E on y axis, that is probability of occupation of electron in energy level on y axis, and energy on x axis. So in that case, what happens? All electrons below Fermi level are, so this is Fermi level, all these energy levels are occupied with electrons. All these energy levels having energy greater than Fermi level are unoccupied or empty. That is the case at T equal to 0 Kelvin. Now, what happens when temperature is increased? So when temperature is increased, we know electrons are making transition from filled states to unfilled states. First of all, the electrons near to the energy levels of Fermi level will make a transition. After that, next electrons. So that we are going to show here clearly. Here T1, T2, T3, three temperatures are taken where T3 is greater than, T2 is greater than, T1 is greater than 0 Kelvin. So first of all, when we give small temperature, in that case what happens? Electrons very close to Fermi level will make a transition like this to the next level. So this is one energy level nearer to Fermi level or below Fermi level. So these electrons which are very nearer to Fermi level, below that will make a transition like this to the next level. Further, when we increase temperature, due to increased thermal energy, some more electrons from one energy level will move like this. Further increase in temperature, electrons in the deeper energy levels also will make a transition to higher levels. So like that, how electron transition takes place from lower level to higher level, or filled states to unfilled states as a result of the given thermal energy. So that is Fermi level or Fermi energy. So based on the above discussion, again we are going to give some definitions for Fermi level. These are the two definitions to Fermi level at T equal to 0 Kelvin. At T equal to 0 Kelvin, the energy level which separates filled and unfilled states is called Fermi level. So these are the energy levels which are occupied. These are the energy levels which are unoccupied. This is Fermi level. So at T equal to 0 Kelvin, the energy level which separates filled and unfilled states is called Fermi level. This is one definition. And among all these filled energy states, the which state is having highest energy? That is Fermi energy or Fermi level. So highest energy level of an electron that is occupied. Out of all occupied levels, this is the energy level having highest energy. That's why it is called Fermi level. That is about definition of Fermi level at T equal to 0 Kelvin. And other than 0 temperature, Fermi level is defined like this. Fermi level is the energy level whose occupation probability is half at any temperature other than 0 Kelvin. Fermi level is the energy level whose occupation probability is half at any temperature other than 0 Kelvin. So like that we can define Fermi level in three ways. Now finally, applications of Fermi energy. So far we discussed what is Fermi-Dirac distribution function, and we analyzed it at different temperatures, and also we came to know what happens when we increase temperature. Now applications of Fermi energy or Fermi function. So the first and foremost application of Fermi energy lies in the case of semiconductors and insulators. Particularly in the case of semiconductors, we know charge carriers are electrons and holes. In the case of N-type, majority charge carriers are electrons. In the case of P-type, majority charge carriers are holes. So carrier concentration we can calculate using this Fermi function f of E. So actually we have one expression, small n equal to integral f of E and z of E, where z of E is called density of states function and f of E is called Fermi function. So this is the place where we are going to use Fermi function. So using Fermi function, one can calculate concentration of charge carriers in a given semiconductor. That is the first and foremost application of Fermi level or Fermi energy or Fermi function. It is used to describe insulators, metals and semiconductors. So based on Fermi energy also we can differentiate metals, semiconductors and insulators. Fermi energy is applied in determining electrical and thermal characteristics of solids. In determining electrical and thermal characteristics of solids, Fermi energy plays a vital role. And finally, it is also important in nuclear physics to study the stability of white dwarfs. White dwarfs are nothing but the materials or the stars whose mass is comparable to the sun, but their size is very small. That is whose radius is 1/100th of the radius of the sun. So to study about the stability of dwarfs, this Fermi energy is utilized. So like that, Fermi energy have so many applications. So that's all for today's session, where we discussed about what is Fermi-Dirac distribution function and what it talks about, and its expression and its analysis at different temperatures. Based on that analysis, we discussed how f of E varies with E, and finally the applications of Fermi energy. So in the next class we are going to discuss about different types of optoelectronic devices. Thank you.